The first talk was about the SPADs. Now I'll go to the other extremes of simple PN junctions. So the talk will be on an on-chip interpolation-based readout scheme for low-power, high-speed CMOS images. I'll motivate you initially with why do we need low-power sensors and how can you obtain low power and speed together. I'll discuss the proposed on-chip interpolation technique, some simulation results, and conclude the section. So this talk is primarily an architectural level improvement in the detection technique, which helps us to obtain low power images. Just to give you a brief overview of what an image sensor looks like. So this is an image sensor with pixels, column decoders, row decoders, and some data converters. Each of these pixels consists of a pin photodiode. So this is a P plus and P. This is the photodiode detector, and 3 extra transistors, the transfer gate, the reset switch, and the column selection switch. So when the light is incident on the photodiode, so this is a depleted photodiode, it generates electron hole pairs. And these electrons are then transferred to the floating diffusion node, where these electrons get converted into a voltage. And when the pixel has to be read, then this voltage is read through the SR switch into the column. This is a simple imager. But why do you need low power images? Now, if you look into the ADCs, the data converter in the image sensor, you can have the data converter on the chip level. You can have a single data converter, which is converting all the pixels data. Now, you can imagine that there's a single data, and as the resolution increases, the bandwidth requirement of this data converter drastically goes higher. The other extreme is to have the data converter in the pixel. But if this cartoon shows that if you have the data converter in the pixel, the photodiode area goes down, or the fill factor goes down, and the fill factor is directly related to the sensitivity of the device. So if you want to incorporate the data converter in the pixel, which can be much faster, however, the fill factor or the sensitivity of the photodiode goes down. So this both are not an option. Somewhere the middle ground is to use column level data converters, which gives the best of both the chip level as well as the pixel level. And to give you some numbers, the chip level you have, let's say 1. For a comparison purpose, I've used a resolution of 2592 times 1944 pixels. Column level you have 2592, and pixel level you have 5 megapixel. In terms of, let's say, power consumption, you see that the pixel level consumes the least amount of power because it's individual converting the single pixel. Therefore, the need for the speed, the bandwidth requirement is very low. However, the power requirement for a chip level ADC is much higher because the bandwidth requirement is also much higher. And somewhere down the line, the compromise is with the column level, which gives us an optimum in terms of speed as well as in terms of the power consumption. However, this power consumption of 39 microwatts is still considered to be higher. So we would like to see what can be done to reduce this power further while maintaining the high speed, right? So the way that people are working out is to reduce this column level power ADC, and there are different architectures which people follow. They try to do some hybrid cyclic plus R ADCs and try to play around. I'll give you 2 examples of how to reduce power using SAR architecture. And also the other way of looking into it is kind of an on-chip compression-based techniques or kind of an algorithmic level data readout-based techniques. So the 2 techniques are, one is the circuit level and another one is the architectural level. So the talk will focus more on the architectural level, not on the circuit level. But just to give you a kind of motivation as to what we are trying to use in architectural level compression. If you see, if I plot a row of this image, the intensity variation, the difference in the intensity that you see over a larger range is very low, right? So, for example, till around let's say 100 pixels, the intensity variation is less than around 10 intensity difference. There is a drastic contrast change over here, and therefore you see this peaks. But let's say over a larger row, the number of pixels in a given row, the intensity variation is still lower for a greater chunk of number of pixels. The question is, do you need to convert each of these pixels? So each of these pixels has analog data. Do you need to convert this analog data into digital? Or you can apply some sort of algorithms by which you don't have to convert each and every pixel data, thereby saving considerable amount of data conversion power. The delta readout technique that are currently proposed in literature, one uses a two-step ADC, wherein the MSB part of the first pixel, and let me just go back. So let me just go back. If you see that, let's take 2 pixels over here, then you see that the 2 pixels have relatively same intensity, and therefore the MSB part of these two pixels will be pretty much the same, right? There will only be a variation in the LSB, but the MSB of these 2 neighboring pixels will be pretty much the same. So it uses the temporal correlation between the pixels, and it simply copies the MSB and only uses the ADC to resolve the lower bits. So the conversion of the MSB, the energy that is required to convert the MSB, is kind of saved. Here also it does the same thing with the SAR logic, and you see that the output of the SAR logic is trying to copy the MSB, so that for 2 neighboring pixels only the MSB gets copied and only the LSB consumes the power. We're proposing a similar kind of structure, but with cyclic ADC. That's because you see that SAR ADC, to incorporate the SAR ADC in the column pitch is relatively difficult. The column pitch has gone towards around 1.1 micrometer in the current sensors, and to implement a SAR ADC at 1.1 micrometer is relatively challenging. Therefore, you have more of column shared SAR architectures. So around, let's say, 10-20 columns using a single ADC. However, column level ADC per se is not available in SAR architectures because of the capacitor mismatch problems that has to be taken care of. So one algorithm that we are proposing, which can help in reducing the power, is to do kind of an on-chip interpolation. So instead of just copying the MSB, if you try to interpolate the MSBs, probably it will give some better results. So this is my pixel array. The pixel array data, the analog data from the pixel array, goes to a correlated double sampling circuit. The correlated double sampling circuit that you are using is pretty conventional circuit. The output of this correlated double sampling circuit goes into a kind of a pixel read or interpolate circuit. Now this circuit decides whether the pixel has to be read or you need to interpolate the data. When I say pixel has to be read, the pixel information is converted into a, let's say, 10 or 12 bit of information. When I say a pixel needs to be interpolated, then not all bits are getting converted, only the LSBs will get converted, right? So you see that here it takes 2 neighboring pixel information, so it uses the spatial correlation between the 2 neighboring pixels. It uses 2 pixel data and tries to find out whether this difference of the 2 data is greater than a threshold voltage. Now, how do I compute the threshold voltage? If you have a voltage span of, let's say, 1.7 volts, and if you use 256 intensity level mapping, then one threshold level corresponds to around 6 millivolts, right? So you can have around, let's say, 5 or 6 intensity levels to say that if the difference between these two is, let's say, greater than 30 millivolts, then the pixel information is relatively different from your neighboring pixel, and therefore I read the pixel and convert all the bits. But if the intensity difference is lower than 30 millivolts, then I say that I will not convert the entire pixel information. I will only convert the LSB information. Once that is decided, so this is a simple cascade amplifier working as an open loop comparator, right? So it's so the difference between these two is being compared with a threshold, and then the comparator tells me whether I need to read the pixel or I will need to interpolate the pixel. So basically, if the flag of this detection logic is 1, then I read the pixel, and if the flag of this detection logic is 0, then I interpolate, and I have an interpolation circuit over here, which is I use a 10 resistive ladder interpolation. So basically, I can interpolate only 10 pixels. So if I have the first pixel and the last pixel, then all the neighboring pixels can be interpolated. This is timing diagram. I think I'll skip it. So I just wanted to show a few more things as to there's a threshold that is important as to what is your threshold when do you say that the pixel information is new, and when do you say that the pixel information will have relatively same MSB information. So we varied the threshold. And we saw that the PSNR kind of decreases as you increase the threshold. That is obvious, because you see that if the threshold is very large, if it's greater than, let's say, 30 millivolts, then you see that the 2 pixel information is relatively different. And if you interpolate these 2 information, then the interpolation and the logic will make some errors. And basically, you'd say that if let's say the pixel threshold is greater than 6, then you would not like to interpolate, rather you would like to read the pixel and convert all the bits. Similarly, you see that the conversion factor also kind of improves as you increase the threshold. As you increase the threshold, let's say you're working at around 10 or 12 threshold levels, then you're converting less number of pixels, right? You're interpolating more number of pixels, and therefore the conversion factor that you get in the pixel is quite high. So the PSNR and the conversion factor are kind of inversely related. What you observe is that for let's say a PSNR value greater than 30, you need an intensity level which is around 30 millivolts. So this is 5 intensity level. The error, so we plotted the variation of this capacitance. So that you see that let's say the functionality of this read or interpolate circuit will depend on the values of this capacitance as to how well you are able to find the difference between two neighboring pixels. So we played around with the variation of these two and checked for the minimum error. And we found out that for around 300 femtofarads, so we get an error which is lower than one threshold level, 6 millivolts. So that was substantial enough. And we also played around the influence of this parasitic capacitance, because you see that we're kind of DC biasing this. So initially, we connect this R to A, so that DC biases the cascode, so it stores to a certain potential, and the difference between the two pixels is with respect to a DC bias over here. So the parasitic capacitance, the variation of the parasitic capacitance over here will play a role. So we try to find out how does the parasitic capacitances influence the threshold voltage choice. And from this analysis, we found out that if the threshold voltage is roughly around, let's say 1.4 or 1.5 intensity levels, which is roughly around 6 millivolts, 15 millivolts, then the error that we get because of this parasitic capacitance is not very high. So in terms of PSNR and compression ratio, we gain both in both aspects. Just to show you some effects, so we used the compression, the interpolated data, and this picture is after obtaining the interpolation, where here we are simply copying the MSB, we are not interpolating the MSB, and you see that between these two images we have around 5 dB improvement in the PSNR or the PSNR of the images. We try to play around and see if we have a noisy image. We added a column FPN with around 2% FPN and see if we can resolve it. We see that even with the 2% column FPN, the interpolation technique still gave a PSNR of the image obtained is around 28.76. The original image had a PSNR of 30.59, which is not bad. So the PSNR saves considerable amount of power. You will see that it saves around 50% of the power when we use direct readout. We also try to see if this can be used for infrared images, and it does. It's applicable for infrared images too, where the PSNR is kind of relatively saved. So in conclusion, what you see is that for the threshold of 5, we obtain around 57% compression is achieved for natural images, and because of 57% pixels are not being converted directly, or only the neighboring pixels are not being converted, you see that there is a power saving of around 48% through an algorithmic mean. So this process does not use any circuit level power saving techniques. It only uses an algorithmic technique. We are also working on the circuit level technique to combine it with an algorithmic level technique to reduce the power further. Because it's saving a substantial amount of power while obtaining around a 57% compression. The compression gives us the speed, whereas the power saving gives us the low power thing of it. I think I'm